Dr. Cook's lab to try and figure out how we can, in our lab specifically, produce these zinc oxide nanowires. So today I'm going to go over some relevance to green energy, what the lab does, some problems we face, some background experiments, and a few results I've gotten within the past few days. So some of you might be wondering where my research sits in the world, and it's in the world of electronics. So we find that in small electronics, you can put these materials, which I'll talk about in the next slide, that are called piezoelectric. And you'll be able to charge smaller devices or create sensors for biological and environmental systems. The biological systems include glucose or any number of things you wish to sense. Some materials that have been studied before are sodium bismuth titanate film. The difference between the film and the nanowire is that the film is denotes a different micron level size of what grows or what the crystal structure looks like. The main problem we face is that the best working material thus far is lead zirconate titanate, which is PZT. The only problem is to make PZT, you need lead, and lead being, when airborne, is dangerous, so we sort of don't want to produce more dangerous lead. That's why I'm focusing on zinc oxide nanowires. So what is piezoelectric material? By this picture you see there's a stress on both the bottom and top, and once you apply the stress, it sends an electrical voltage across the axis, the same axis as these stresses, which you can register on voltmeter. The lab itself tries to put these materials into different systems, studies the properties of these materials, and makes sensors and devices based solely on these materials. The one section of this lab I'm working on is looking at the dielectrical and piezoelectric properties of zinc oxide. So we can use zinc oxide, since it's a nanowire, we can use it for the sensors, because you can't use film, since it's too large to register very small quantities of sensitivity. It also can be used as a dielectrical material between a parallel plate capacitor for energy harvesting. So I want to find out, how do we form these crystals, and once we form them with a specific fabrication process, because if you don't know what variables you wish to change until you know how you're making materials, I want to know when I have a sol gel, what the viscosity has an effect on the zinc oxide nanowires, and what the roughness of the substrate, the thing that you grow the wires on, what effect the roughness of that substrate has. So I've been talking about zinc oxide, and you haven't gotten a good picture of, okay, there's this material, has zinc and oxygen. Well, not really. Under a regular cubic cell, the highlighted oxygens and zincs, there are 4 of them. So it simplifies into 1 zinc and 1 oxide per each other. But if you look at the lattice structure, you end up getting this 2 by 2 which then when you rotate it, creates this hexagonal pattern, and that way it creates a voltage potential with stress or strain, or it creates stress or strain with a voltage potential. And at a micron level, you see here, you can you get this crystal structure within these wires, and the wires are nano-sized, but the entire layer is on the micron scale. The differences in wire for this one were a change of ratio between how much zinc precursor and how much oxide or hydroxide in the general case was used. So there are different techniques, as I said before. The problem is some of these techniques use too much energy, such as the vapor-solid synthesis, use too many ingredients that, or too many chemicals that are just thrown away, like the chemical bath deposition, or don't produce these nanowires in the crystal structure you wish them, such as treating a substrate with a spin-coated seed layer, or the sol gel, what I was talking about before. So I focused on using the sol gel process, the spin-coated seed layer, and the hydrothermal process synthesis, since the hydrothermal synthesis uses a device called an autoclave, which is already commercially used to make crystals. So the sol gel, what it would do in this case, it would prevent delamination. You'd be able to grow the crystal structure on smoother surfaces, but the way you describe the sol gel is with the viscosity, and the way in which you might want to change the viscosity is altering or increasing the amount of time you mix the sol gel for. It's been done before in barium strontium titanate, BST, and what it does is the thicker or the more viscous the gel is, the more crystallization occurs, which in this picture you'd see, this isn't the experiment itself, but this is a nanowire. So you see how dispersed it is. It's thicker here, more dispersed over this way. So with a more viscous sol gel, you'd expect to see something like this in zinc oxide, and you'd also see thicker wires with a less viscous sol gel. You'd expect to see less. The substrate roughness was looked at before of zinc oxide. So far, we believe it has to do with the orientation. As you saw before, the piezoelectric materials stress strain is best utilized when it's parallel to where the voltage comes out of. So the wires being straight up at the C or Z axis, you would want a rougher substrate, which causes this erectness. The other part is it increases the crystallinity. So here's a general picture of what my methods so far look like. Here are some preliminary methods. You'll see some places I'm measuring, some places I'm mixing or spin coating or putting stuff in hydrothermal. So I'll explain it bit by bit. So step 2 and step 4, I would use the zinc acetate dihydrate, which is the zinc precursor, and the potassium hydroxide, and each of them you put in methanol, and after heated, you mix them both, which would create the sol gel precursor. You'd essentially create a polymorphous zinc oxide. And it's not the nanowires themselves. After you make this, you spin coat it such that the you'd get it onto the substrate evenly. The only problem with spin coating is, so far as you'll see next, is it doesn't disperse it as evenly as we wish it to be. So another part of this is the hydrothermal method. Here we use zinc nitrate hexahydrate as the zinc precursor. We use HMTA as the hydroxide or oxygen precursor. And PEI is more to etch out the wires. It's used just as an added plus. You can do it without PEI, but it's you get better formation with it. You put the autoclave, you put the materials in the autoclave in the furnace, and then heat it. The three different measurements, or measurement times I'm using are before the substrate has the sol gel on it. I want to get a look at how rough it is. So I use atomic force microscopy. After I create the sol gel, I want to change the viscosity. As I said before, viscosity is important, so I want to change it by dilated hours time. And so far, I haven't been able to do this because I need to first replicate results that have already occurred in labs. And after I create the zinc oxide nanowires, I go to this step, which are the numbers I wish for. That step, you'd see here, I use SEM imaging, or scanning electron microscopy, to look at the morphology. So those pictures, the black and white pictures you saw before, show what the nanowires may look like under this imaging. I use a piezometer to find D33. That's the constant between the electrical voltage and the stressor strain, which are parallel to each other, going about the same axis. The D31 is the constant between translating the electric voltage to stressor strain, except the stressor strain in this case would be perpendicular to it going this way, creating certain friction in the wires themselves. I want to look at how it can be used in parallel plate capacitors as a dielectrical material to store or harvest energy and see how much charge it can maintain. I want to look at the decomposition of the material, and by looking at tan delta, which is the dielectric loss, I can see how many electrons or how much energy it stops being able to harvest or produce after a certain amount of time you're using it. I use an impedance meter to look at the resistivity, or the amount of current, real current, that can be stopped within a certain length. And I want to find impedance, which is almost the same measurement, the amount of current that can be stopped within any material, but for not real or an alternating currents, where you get imaginary numbers. So far I've looked at what is in the gel, and I said before, you see the different dispersion, you see this small dot, this big dot here. That dot forms because of when we put it in the spin coater, it sucks up the substrate, the thin film, which is in this case stainless steel, 25 microns thick. It would suck up the substrate and create a bowl at the bottom of it. That's a problem I have to try and face. But we looked at different points on the same substrate, like say take a point here, 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 and that's what each one of these sample points is, and not different substrates. So as you can see, the differences in numbers, it varies from like 29 to 0.8 for capacitance of in nanofarads, for example. This is because the dispersion of material isn't done evenly, and that's something I have to fix. I also looked at the roughness of the substrate. Here you can see an AFM image done with on a contact basis. The deflection